Hello, everyone. I'm Martin. I come here from Prague, from the University of Chemistry and Technology, but I'm a postdoc also at the University of Leiden, where we work on a couple projects related to general drug design, and we also develop some open source software, which I'm going to talk about briefly. So just about a little bit about general drug design. So yeah, that's not a new problem. This has been tried since the old ages. Basically, the papers that we can read today, they look very similar. Just the graphics are improved. And usually we look at the a little block of AI somewhere in the middle, but yeah, you still get that kind of the same ideas and same approaches, but just different tools. So what basically my mission is for this project is to figure out some ways to explore chemical space a bit more efficiently, and more efficiently meaning put molecular generators to practice or use de novo drug design techniques to get from basically virtual ideas to real material that we can test in assays as quickly as possible. So we basically tried a few, we have a few projects where we tried different approaches. So what I'm going to talk about today the most is using our molecular generator projects. I will get to explaining it later. But we also have some basically reaction enumeration projects that basically assume some in-house chemicals, in-house building blocks, or something that's purchasable. We combine it and then screen it, and then we pick out what we can actually make in the lab and test. There's one approach is basically what we see down here. What I'm going to talk about today is basically trying to combine different objective functions, especially focus on synthetic accessibility, which is this LED-free score that I'm going to talk about later, and basically guide the molecule generator towards a virtual library that is more synthetically accessible and therefore more readily available to the medicinal chemists to consider. So this is actually not my own effort, so it's a collective effort, so there's a lot of people to thank at the end. And this is basically the software stack that we're working with. So the case studies that I will be presenting today, they use one or more of these. So some of them we're still working on. For example, this for structure-based design still not available, but it will be soon. We have a graphical interface that we're working on as well for molecular generation. And we have for T-cell modeling, which also is an objective function here. We have this package QSPR-PrEP, and of course, drug access for IDEA. So about projects. So this is basically a collection of different models that use what is called reinforcement learning. So in reinforcement learning, you basically iteratively try to teach the model to generate molecules that you want based on a certain set of objectives. So in Redis, we use Pareto optimization to basically find the perfect balance between different objectives. And basically, the training goes like Redis generates some compounds, we score them, give feedback to the model, and then we try to reinforce the ideas that it generates that satisfy our objectives. We also have something that's called the exploration parameter, which basically allows you to fine-tune a little bit the exploitation feature of the model. So about the objectives that we used in this particular project, which was to design some new ligands for monoglyceride lipids, which is an interesting enzyme. I'm not going to get into the biology here. And what we wanted to do in this project is basically validate some customized synthetic accessibility scoring, something we call LED-free score. So this is basically, if you're familiar with ARIE scores, this is conceptually similar, but we try to build different models for different sets of building blocks that are available to our synthetic software. And then, of course, we use a QSAR model for the bioactivity prediction. So the model needs to find the perfect balance between these two. And what is basically embedded in the LED3 score itself is whether we can find retrosynthetic group with AISIN finder or not. So you can basically solve some molecules. They can be from Campbell, or you can do some smart clustering on different data. And then a set of building blocks, you solve them with AISIN finder. And then for each set of building blocks, either they come from your in-house set or they come from Zinc or whatever. You train a model that will tell you, like, with these building blocks, am I able to find a representative? So was basically the idea that we tried to do in this project. So we designed basically 6 different experiments. So we trained DrugX with different synthetic accessibility scores. So either we use none, so that means we just use the PSAR model as an objective, or we use the well-known essay score by Peter, who's also here, or we use these machine learning-based scores. So the models labeled LED3, that's basically on our in-house building blocks. So we solve roots with in-house building blocks, either from this clustered set that comes from public data or just random set from Campbell, and then same for Zinc building blocks. So this is basically what's commercially available. And yeah, I don't have the data here, but the Zinc set is obviously much larger than what we have in the bridge in Leiden. So if you ever use RScore, so this model is basically more or less equivalent to RScore in the idea of it. And then we generate 100,000 structures for each of these 6 cases, solve the roots with AISIN finder. So for every single combination, we solve 100,000 roots, and we determine the desirability of the generated structures based on our PSAR model, and we answer some of the questions that we have. So how many desired compounds with actually solved roots that we can show to the chemists can we obtain? What is the prediction error of these machine learning-based scores on generated molecules, which actually is quite interesting to look at. And then, of course, the ultimate validation can actually pick a few new compounds that we can synthesize and test and validate experiment. So, yeah, this is a bit of a confusing graph, but I'll have to walk you through it. So the color means different building block sets. So for these 100,000 molecules, we can solve the roots with using different building blocks. So either we can use the in-house LED3, so then we can find roots that only incorporate our building blocks, or we can use the Zinc, so anything that's purchasable. And then we can look at if the molecule was actually solved with those building blocks. So that's this like faded color, and then we can look at if it was solved, but also predicted active by the PSAR. So we can see that, yeah, DrugX, like if we don't give it any synthetic accessibility score to use, then yeah, we will exploit the PSAR model, and you will not get anything synthetically accessible, so you cannot solve like almost any roots. Now with essays for at least for this project, it was quite hard to balance actually the PSAR model predictions and solvability. So you get really good solvability, so good synthetic accessibility. So a lot of the molecules you can actually find roots for, they're rather simple. But in our case, we were not able to get active predictions for them. So that was interesting. But in other projects, essays actually worked for me quite okay. So I don't know what happened here. And then for the machine learning score that are basically tailored to your desired building block set, then yeah, the performance was quite okay. And we were able to get actually good trade-offs between solved and active. And what's interesting here to notice as well, it doesn't matter much if you use the large building block set from Zinc, which is a few million, or the I think a few thousand from the in-house LED3. So you get basically the same solvability. So that was very interesting to find out as well. So that's for question number 1. Then for number 2, how predictive how predictive are the models, or how reliable are they actually on generated molecules? Because generated molecules, they come from different chemical space kind of. They have their own specifics. So once you validate the model, you actually use Campbell data, or we use Campbell data, so real molecules in the real database. But if you try to then predict on generated space, then what is actually the performance drop? So that's what we are looking at here, and yeah, quite a bit actually. So these are for different classification methods, different errors, and the differences between the test set result and between the generated space predictions. So because we solve routes for all of these generated molecules, we're able to calculate this metric. So then, yeah, of course, the applicability domain is is different. So this was also interesting to look at. So yeah, if you're using some machine learning store for the network design, you need to be aware of this error. And then for the first question, yeah, we tried to synthesize 3 molecules that were suggested by the model. And we, of course, applied some filters. And we were actually able to find some like moderately active. It was not as novel as maybe we would like, but yeah, it was quite interesting. It actually gives a new idea to the pipeline. So that was one project. And then for another project, I will talk a little bit about chemokine receptors and so maybe a different approach that you can take if there's not enough data to do QSAM modeling. So chemokine receptors are actually quite interesting biologically. So they play a role in metastasis of cancer because they can recruit tumor cells to go to the lymph nodes, which is something we don't want. So basically, disabling these chemokine receptors is quite important. So this is how they normally operate. So they are recruited by these chemokines, which are proteins that bind. So they are GPCR. They bind on the outside of the cell. Then they activate the GPCR. So one obvious way is like targeting this orthosteric site on the outside of the cell with a small molecule. But what we're trying to do in Ligand is actually target this intracellular site on the intracellular site, which is an allosteric site that blocks the signal in a bit different way. So it doesn't have to actually compete with these chemokines. So that's our target. And again, similar workflow, but this time we're going to use molecular docking because we cannot do QSAM modeling. So we decided as one of the objectives to use docking and some feedback from it to basically build a model what kind of molecules we'd like to see. But otherwise, everything is the same. We just use the zinc starter because we can also look at the purchasable space. Luckily enough, for CCR2, which is the subtype that we're targeting, there's a crystal structure with a ligand in place. So you can get some idea about what's sort of subpockets you have and how your ligand should bind in this pocket. And there's actually a couple of different scaffolds in the literature that are quite different. So you can also do docking. There's no crystal structures for them, but you can do docking and kind of decide on the poses if they're good or not. I couldn't find like IC for this compound, but this is actually from patent literature. It's a clinical candidate. So then, yeah, we can basically look at how each compound does, what kind of interactions there might be, yeah, basically the poses look fine and make sense. So what then I did in terms of designing this scoring function is because these scaffolds, they were explored, there was some SAR around them. So I took basically those 3 and 5 most active compounds for each scaffold. I looked at the interaction fingerprints and tried to find the most important interactions basically, and then derive some weighting scheme around that, so that we can basically say how many desirable interactions we get, and we have some required interactions, so this mostly like hydrogen bonding with some conserved residues. Then we have some essential ones, which is those that we think enhance activity. There's some DSAR, and then some important ones that only occur like sometimes, but quite often. And we also think that they could be important. and then some maybe interesting new interactions that have lower weight, but maybe you would like to see them in the compounds, just to enrich the chemical space. But important thing to realize here, depending on how you choose these couples, you can get different rankings. So this is very arbitrary score. It can take very different forms. But I think it's like very intuitive and very interpretable. So when you get your results out, you run the interaction fingerprints, you plot your poses. You can basically kind of interpret how the algorithm thought, what went good, what went right, what went wrong. It's like that. So this is how it went in one particular case. So again, we performed some filters on the generated 10,000 molecules here. This is how the training went. So the blue line is actually the more important one. So this is the desired ratio. So that means these are the molecules predicted as active and also as synthetically accessible, and we were able to get retrosynthetic groups for them. So after some, so yeah, we can see that the model is not optimizing quite well here, but still we get some enrichment in the molecules that we want. And there's also, it's also showing like some problem with the drug X as well. Sometimes there's no penalty for non-unique molecules. So sometimes when the optimization is a bit harder, it just tends to output same molecules over and over. So this is what you can see here. But we use early stopping. So once the desirability does not actually go up, we stop. So that's why it cutoffs here. But yeah, in the end, after some filtering, we obtained basically 96 structures that we docked because we use docking as a scoring function. So we could extract the poses for them and basically look at them manually. And with the help of medicinal chemists, we were able to find basically like two kind of easy to synthesize molecules too hard. I can't show them show the structure yet because we don't have the biodata, but they're quite novel scaffolds for this study. So yeah, if fingers crossed that biodata shows up some nice result, with some IP. We also ran some molecular dynamics simulation with the Schrödinger's plasma. So this is for the reference ligand, how it kind of should look like. So we have a nice kind of stable trajectory with all the interactions in place. So this is the concept of hydrogen bonds. We also have some interaction with this arginine, and then some kind of important lipophilic interactions with this string. So we have some candidate. So for this candidate, I'm not sure you the structure, but yeah, we observe basically kind of the same patterns when we look at the MD trajectory. There's some flexibility with one part of the molecule, but yeah, that's easily explained, but otherwise it doesn't move around much. Likes to stay in the pocket. This is just the C-circularia reference for comparison, so we get like similar things. And then for the other candidate, also like a little bit more fuzzy, a little bit more dynamic, but again, like most of the interactions they maintain, and we get a little bit better occupation of the lipophilic pocket here because we have more lipophilic interactions over the course of the simulation. So again, for reference. So yeah, that's the two projects that we did for the design. So hopefully this one also will reveal some new ideas. And now I want to talk a little bit about the software stack that basically that made this possible. So like I mentioned, we developed a few packages for not only general drug design but also USAM modeling, structure-based design. So if it's not it's not yet public. But even in such a small group as we have in Leiden, when I came there, everyone had basically their own scripts and their ways of doing things. And sometimes projects would get started by students, then they would get some result, and then another student would want to use their code, and then the student would again have their own style of coding. So there was some incentive to actually standardize the things that we do, and because we were all doing like basically the same thing, different ways. So we thought maybe let's make a package that would basically take all the things that we need to do over and over again and just do it. And then if we supervise students and we say, hey, you use the QSPR package to do this model, we all immediately know what they did and where to look for results, where to look for the models, things like that. So that's how basically QSPR came to be, where we had several students just building QSAR models different ways. So we were like, okay, let's just put everything together. And from that, yeah, there came the need to kind of course, store different molecules, process them somewhat efficiently, try to build different models in a systematic way when you want to try different descriptors, you want to try different combinations of metrics that you want to compare, maybe do some resampling so you can get maybe a statistical significance testing to test like which model actually is statistically better, things like that. But also what's maybe most of the open source packages we looked at did not solve that well or that comprehensively is when you want to use QSAT models in practice, you also always need to take into account how the molecules are standardized, or what actually the pipeline for calculating these descriptors. So if you want your prediction to be reliable, you need to do all these steps. So that's why we integrated this into QSPR as well. When basically you want to build a model for prediction, it knows the standardization procedure that it was used to, and you can just drop smart in it, and it will standardize it as it was during training, and you don't have to think about it. So I think that's quite nice. Yeah, now we basically try to incorporate all these ideas into this ChemStore interface where we manage standardization, unique identification, basically kind of like a Python API for molecular registration. And we also provide some APIs that you can replace with different backends. Like you can use multiprocessing, you can use DAS to run some calculations. And we're planning now, we're basically just using Pandas table that are get saved into files. So it's easily readable, but you can imagine that this storage, can be implemented in different ways. So we're planning also like some different adapters for different services. And then you can all this Python code, as long as you adhere to this ChemStore interface, you can use all this to get some results real fast. So if you want, you can go to QSPR 3/dev. So this is still under development. That's what we're working on. But there are already some tutorials on how to use this, the ideas that we would like to have implemented. So if you have any suggestions, feedback, or you just want to check it out about how we think about things, we would really like to get some eyes on it, and maybe even you can contribute or something like that. So yeah, with that, I would like to finish my presentation. So yeah, AI, new methods in de novo drug design, they have a lot of potential, but validation for real projects is really important. So that's what we try to do, is make it easy to come up with a computational workflow to do de novo drug design with either docking, QSAR modeling, or what have you. And then basically show the result of the medicinal chemists as soon as possible. And what we really learned that like good software development practices, they do help a lot, even in moderately sized groups. If you have good tutorials and you have some GUI to communicate your results to medicinal chemists, it goes a long way. And also continuous integration and testing is also something that helps to find errors quickly and not have a student really like try to figure out the bug on their own. That's actually find it out during the development. So this is also very important. And in QSPR, we actually also have model consistency tests. So if something changes in the package down the line, and you no longer get the same predicted value, it will get flagged by the tests as well. If you build the same model with the same data using the same random seed, but something else changes, you will know about it. And yeah, so that's the end. So I just wanted to point you to our student sponsor who's working on benchmarking molecular generators. And I would like to thank everyone who participated at any part of this pipeline and the organizers on you for listening. Thank you.
Yeah. Okay. I have a question regarding the synthetic score that you found. You mentioned that you simplified 3 molecules. How many you attempted to simplify?
Okay, so the question was for the synthetic accessibility score. We synthesized 3 molecules. So the question was how many did we actually try to synthesize? So yeah, we did try only those 3. So when we filtered the data, we obtained like maybe 2,000 structures that satisfied some of the criteria, but that's too many. So then we reduced it to only reactions that had 4 steps. So that helped to narrow it down. And yeah, like maybe you saw, those were really simple reactions. So the chemists, they actually picked the compounds that they liked based on the synthetic route that was solved. So yeah, we attempted 3 because they were confident that they can make them. Yeah, thanks.
I'm curious about the pipeline for doing standardization and all that for getting molecules ready. So there's a couple of projects out there that attempt to do that in the context of Cytogen. Looking away Cytogen will and that's the right name, right? There's another one that somebody did.
Yeah.
I get them all.
There's also psychic fingerprints now. Very similar.
You had a very good idea that imitation is this computer form of flattery. Anyway, did you look at that? Because it would be interesting to see if instead of rolling your own and creating another one, there would be a way to see back into that so it's more friendly.
Yeah. Yeah, so yeah, there's actually there's a preprint, but the paper will come out soon that will include a table, like basically of all the most recently developed tools and the features that they have. And what we found out, yeah, there's a lot of tools that do basically 1, 2, or 3 things right, but then they omit the other stuff about QSAR. So what we try to do is basically do one package that can sort of do everything right. So, or like try to get everything sort of like into a complete package. So our target was mainly completeness and also maybe documenting the code more properly and also provide these integration tests and especially the like consistency checks and more consistent setting of random seeds, so you get reproducible results. So yeah, we had more objectives in mind than just the proper standardization. So yeah, like there are definitely scikit-mol is one of them, but I think 2 or 3 more packages that also do this. When you build a model, then you also package the standardization and preparation with it. So it's not our own. Only our own idea.
Okay, I mean, there's multiple approaches to this toolkit doesn't for this tool doesn't do what I want it to do. With open source, one thing away is just add the other one instead of starting a new one.
Yeah, I mean, we could have done that, but it still did not like we had some our own requirements.
Yeah.
That yeah, we just did not, because it takes some time to because we did not actually think this would grow into this. We thought, okay, let's just put a few scripts together, but then it started to sort of like yeah, exactly. So it started to like grow a little. So yeah, that was also like it was kind of natural that it became what it was.
Thanks.
Okay, okay, so thank you.